Hello, everybody. Waiting for my webcam to start. There we go. Sorry I was a minute or two late starting. I had someone knock on my door right before the class was supposed to start. One of the benefits of remote teaching is being interrupted, I guess. So, what are we talking about today? Look at this. We are starting reinforcement learning. Reinforcement learning is one of my favorite things. I think that my heart really lies in the heuristic search side of things. I really love heuristic search. Oops, my webcam. But it turns out reinforcement learning is in a way related to heuristic search, but we'll see as time goes on. It's more related to search than people think that it is, especially the type of tabular reinforcement learning that we're going to be doing. But rather than hype it up too much, let me just show you. So let's start talking about reinforcement learning. Oh, before we get started, someone has a question. When is the Connect 4 competition? So I am going to hold the Connect 4 competition during the Remembrance Day thing. So this lecture right here in, what is that, 2 weeks from now? Yeah, 2 weeks from now is when I'll hold that. I'll give the markers enough time to mark the assignments, and then we'll gather all the assignments and we'll do it then. So hopefully that's not too late for everybody, but I don't want to take up an actual lecture with that, but we'll do our sort of missed lecture. It'll be an optional thing if you want to tune in and see that. Okay, let's swap over to our PowerPoint and we'll see what reinforcement learning is all about. So, lecture number 13, Introduction to Reinforcement Learning. So first, I wanted to mention that the reinforcement learning textbook for this course is optional, but it's also available online for free. So if at any point you are having trouble with any of the topics in reinforcement learning that I have put in the slides, if you want a little bit more information, or if you want to go read this to understand it a little bit better for the exam, you can by all means go and read this textbook. It is the best textbook I have ever read, hands down. Nothing even comes close to how good this textbook is. I was very lucky. Richard Sutton, one of the grandfathers of reinforcement learning, and also a professor at the University of Alberta, I was lucky enough to actually take the reinforcement learning course from Rich Sutton while I was there as a graduate student. So I was very lucky to do that, and he wrote this textbook along with Andrew Bartow, and it's just really well done. It's very understandable. It's got intuitive explanations. I highly recommend it. So for example, if we introduce a topic, and we talk about it in the lectures, you can go read that chapter in the book. Now, it's not 100% necessary. As I've said before, I am keeping this course so that if it's in the slides, that's what you have to know. But the textbook can really help you understand it better, for example, for questions on the final exam. And there will 100% be at least 2 or 3 questions about reinforcement learning on the final exam. So, what is reinforcement learning? So reinforcement learning, or RL as I may call it to shorten it a little bit, it's a sub-area of machine learning. And so reinforcement learning is inspired by natural systems and psychology. And what it does is it sort of mimics, well, the way I like to put reinforcement learning is it's sort of the way that humans and animals learn, and that is via interaction with the environment. And so what happens is your agent that you've designed is going to do some actions in the environment, and those actions will get some sort of reward from the environment. Good actions, and we'll talk about what good actions mean and bad actions mean in a little while, but good actions are going to give you a positive reward, and bad actions are going to give you a negative reward. And the reinforcement learning agent's goal is to maximize the good rewards, okay? So over time, it's going to learn which type of actions gave it good rewards, and ideally, over time, it's going to select those actions more and more often. So that is the concept of reinforcement learning at the highest possible level. So what we're going to do in this lecture is kind of like assignment 2. In assignment 2, lecture number 2. In lecture number 2, we gave a ton of information and a bunch of definitions, and then later on throughout the course, we used those definitions so that you can get used to them and see examples of them. In this lecture, what we're going to be doing is introducing all of the terminology about reinforcement learning. If you don't understand it all right away, that's fine, because we're going to be taking each of those as the next few lectures unfold and going deeper and deeper into those terms so that you will come to understand them through the math and through the examples that I give. But this is sort of the overview terminology lecture before we dive into all the details. So machine learning. This is not a machine learning course. However, it's nice to know sort of where reinforcement learning lies within the broader topic of machine learning. So within machine learning, there are 3 main groups of types of learning that happen. Probably the most popular is supervised learning, followed by, and then there's also unsupervised learning. I'll give the details of supervised and unsupervised learning in a bit. And then there's reinforcement learning. And so they're sort of separate topics within machine learning. You pose the problems in different ways. There are different algorithms that can be applied to each of these 3 types of machine learning, and we are going to be dealing with reinforcement learning only in this course. Now, at the very end, we'll talk a little bit about neural networks that can be used for supervised learning, but we'll leave that until the end of the course. So machine learning. As I said before, machine learning is divided into these 3 topics. But the 2 that we won't really be talking about, but I do want you to sort of understand, are supervised learning and unsupervised learning. So in supervised learning, what happens is you learn from training data, right? So I give you a bunch of data. So for example, I give you a bunch of pictures of animals, and I have labels of what type of animal that is. So this is a picture of a cat. This is a picture of a dog. This is a picture of a goat or a ferret or whatever. And so you are given inputs along with the ground truth outputs. And what happens is whatever supervised learning algorithm you're using, whether that be, there's 100 of them, there's 1,000 of them maybe. Neural networks have gotten more popular as time has gone on, but essentially what you're doing is your algorithm is going to learn to predict the outputs for new unseen input samples. So for example, after you've seen 10,000 images of cats and 5,000 images of dogs, you're going to be able to, given a new image, hopefully be able to say, that's a cat with this probability, or that's a dog with this probability. So that's what supervised learning is. And it's not just cats and dogs, but there's all sorts of problems that fit into that category. Unsupervised learning, on the other hand, it's got no real strict definition like supervised learning does, because unsupervised learning, you're going to give the computer some data, and whatever algorithm there is, the computer is going to learn something about that data. It's not necessarily going to be given labeled outputs or anything like that. It's just going to learn something. It's either going to find a pattern or find like, okay, this cluster of data, these are all similar inputs. This cluster of data, that's all similar inputs. So the canonical example of unsupervised learning would be, say, a clustering algorithm, or so you could give, let's see, an example. You could give an unsupervised learning image problem as well. So for example, if you did give it a bunch of images of cats and dogs, but you never said what they were, maybe the unsupervised learning algorithm would say, hey, there's something interesting and similar about all of these images, and there's something interesting and similar about all of these images. Maybe it's the fact that there's a lot of the color red in this image, or a lot of the color blue in these images. Or maybe there's a shape over here that's common, or a shape over here that's common. But unsupervised learning does not learn from the same type of labeled data. It sort of tries to figure things out on its own. So supervised learning in machine learning has a sort of workflow like this. So you have some input data, right? Maybe images of fruit, for example. These are images of fruit. And so you have some sort of supervisor. The supervisor is the thing that says, here's what this data is, right? So you might have a supervisor which is a human, and the human is going to look at all the images of fruit and say, this is a tomato. This is a pear, this is a peach, this is an orange, right? And so you take in the data set, which is a bunch of images, and some supervisor who knows what they're talking about, that's why they're called the supervisor, is going to assign labels to those. And so you've got some algorithm, it could be a neural net, it could be geez, it's been so long since I've done any supervised learning. Some sort of tree structure, whatever you want, as support vector machine, whatever, some algorithm is going to be passed in the data as well as the learning samples. It's going to go through some processing. This process is going to be called the training process, and the algorithm with the parameters that it has learned is going to be called the model. And so if it's a neural net, then the neural net is called the model, and you're going to be training that model. At some point, you've trained the model well enough, and you've got a model that you can pass in some new input that you don't have a label for, and the output, the algorithm is going to say like, hey, this is a tomato, hopefully, right? So it's exactly what I described before, but in a little bit more graphical detail. So some types, the supervised learning itself can be broken down into two main types. One is classification. So classification is what we just talked about. There's a number of different classes of the types of input. These are discrete classes like tomato, pear, whatever. And there's also a type of problem called regression. And you've all seen probably regression before because you've all seen these line of best fit problems. And so if you try and find like the line of best fit through a bunch of data, this is a supervised learning problem. And the way this differs is the fact that it's not a classification problem. You may have a real valued output space rather than a discrete set of possible outputs. So here, for example, the training data is a bunch of X and Y values. So let's say you've got, this function might be y equals x cubed minus 10 plus 6 or something like that. And so you train the algorithm with a bunch of inputs and outputs of that actual function, and then eventually, hopefully, your model will learn to mimic that function for any given input. And slowly over time, as you learn, you can actually watch your function become more and more accurate over time. Unsupervised learning, on the other hand, this is an example that I should have said before, but you've got a bunch of data and your algorithm learns to cluster it somehow. So this is a really cool example where you've got a number of different digits that were input into the unsupervised learning algorithm, and you've said, okay, classify these somehow visually. And so you can see that there's a number of different clusters here. So these look like all 2s, these all look like 8s, these look like 0s, these look like 4s, but there's some error there. So like one of these 4s is actually a 9. Whether or not it's correct or not, this whole algorithm's point is to just cluster that data. So that's supervised learning, and that's unsupervised learning. And the only reason I want you to know about those is so we can say what reinforcement learning is and how it differs from those types of learning. So first and foremost, reinforcement learning as a concept is not an algorithm. It is not a specific algorithm. My way of looking at reinforcement learning is that reinforcement learning is more of a problem specification. Okay? So many different algorithmic techniques can be used to solve reinforcement learning problems, but an RL problem is a way of framing the type of optimization that you want to do. Okay, and we'll see that as we go into the details of reinforcement learning. But for example, you could have a problem like pathfinding, right? So you could have the problem of pathfinding. You could apply heuristic search. Let's say you can apply A* to solve that problem. You could apply a genetic algorithm to solve a pathfinding problem. You could also apply reinforcement learning to solve a pathfinding problem. And that'll actually be assignment 5, is to kind of do assignment 2, but with reinforcement learning. And so reinforcement learning is a way of specifying the problem so that reinforcement learning methods can solve that problem. So we've got a bunch of different algorithms that we may be able to apply, but they are only applicable when the problem is framed within the reinforcement learning framework. Okay, so we'll see what that means. So RL is learning via interaction with the environment. Unlike supervised learning, there is no explicit teacher for the learning. There's no person that says this is right or this is wrong. What's going to happen is the agent takes some actions and then it receives a reward signal from the environment. And learning via interaction teaches us about cause and effect, consequences of actions, what to do to achieve goals. It teaches us all sorts of cool things. So in the most basic example that I can think of about taking an actions and receiving a reward signal is if you touch a hot stove. You touch something that's very, very hot, right? I take the action of putting my hand on the stove. The environment then, and the environment includes like the nerve cells in my body, it's going to say, holy crap, that's a really negative reward. You burned your hand. That really hurts, right? So pain is a reward signal that says, don't do that again. That's very painful. On the other hand, if I go get a massage or something, that's going to be a very good reward signal. It's going to feel good. I mean, I guess there's some massages that don't feel good, but generally, something good that happens that makes you feel good, the serotonin gets released or dopamine or whatever it is, you get a positive reward signal from that. So you're going to do something, you're going to get a reward signal, and then you're going to learn basically to do the good things again and to not do the bad things again. So here's what that sort of looks like. You've got an environment. That environment has states, actions, and rewards. And you've got an agent that is interacting with that environment. So the agent is going to take some action. That action is going to update the environment to the next state. You can see how this is similar to things we've already done before. But the new thing is that you're going to get a reward based on that. And then based on that reward, there is some internal way of us mapping actions to reward values. And then we're going to take good rewards more in the future and bad rewards less in the future. So for example, another example here, we've got some environment, the agent, maybe the agent is the dog here, and the dog figures out that when I wag my tail, my human throws the stick, right? So whenever I wag my tail, that's a good thing happens when I wag my tail, right? Or maybe the dog says, when I pee on the carpet, the human gets upset. So maybe I don't want to pee on the carpet anymore, right? So this is literally what's happening in our algorithm. It's conceptually very simple, but the algorithms can get a little bit complex, but we'll keep it simple in this course. So what this does is it forms a loop, and this loop repeats basically for however long you want the training to occur. So just like we had with the genetic algorithm, we're going to loop and loop and loop until we stop for some reason. The same thing is going to happen in reinforcement learning, but the loop is going to look a little bit different. So we start off up here with an agent. The agent is going to take an action at time step t, right? So we're going to have time steps. Just like we had generations in the genetic algorithm, we're going to have time steps of the state of the environment. So we take an action at time step t. That action produces some change in the environment. Either I move within the pathfinding, I throw the stick, I touch the stove, something happens to the environment. Then, what gets produced from the environment is the next state. Oops, I forgot to say the next state over here, or the original state. So we're in a state, state t. We take an action at state t. That produces the next state, and it produces a reward. And so that's just going to keep happening. And that reward, it's going to update our belief of what we think are good and bad actions. Then we're going to take a new action. We're going to get a new reward. We're going to update our belief. We're going to take a new action. We're going to get a new reward. We'll update our belief, etc., etc. And that is the main loop that we are going to be programming in assignment 5. If we want to take a little bit more of a technical look at this, then let's define this exact sequence of actions that happens. So the agent and environment interact in discrete time steps. So the first time step of our algorithm is going to be time step 0. The next time step after we've done an action will be time step 1, 2, 3, 4, all the way up to some termination condition. So the agent observes a state at step t, right? So this is the definition that we're going to be using. So that is S sub t, which is a state at time t, which exists in the set of all possible states of our environment. Then the agent produces an action at step t. That is little a sub t, and that exists in the set of all possible actions at a given state, right? Because there are actions that are possible from some states that are not possible from other states. Then the environment gives us the resulting reward. So that reward is rt plus 1, so that's the next reward, and that exists within the real numbers, right? So we get some real valued reward from that, and then we transition to the next state. And so we have st plus 1 exists in the state of all states. And the textbook, gives a really cool diagram of this. So what it does is it says at state s sub t, we take an action a sub t, that gives us a reward, rt plus 1, and transitions us into the next state. So these big circles, those are the states. The link here is the action, which gets us a reward, and that gets us to the next state. We produce a new action, a new reward, new state. State, action, reward. State, action, reward. State, action, reward. That's the main loop. We can apply this to games as well, right? So it's not just the environment. Of course, the environment could be a game environment. So if we have some game playing environment, we are going to say, okay, I think I should push these buttons at this state of the game. It affects the environment. We get a new state. We get a new reward. There you go. So the overall workflow of the reinforcement learning problem specification and training, it works like this. We're going to be operating within some environment, right? So whether or not that's a robot in the real world, or it's an agent in a video game, or it's our agent in assignment 5, we have some environment. We have to define some reward, and we will talk about reward because reward is very, very important. Reward is to reinforcement learning like the fitness function is to genetic algorithms, okay? So the reward tells us what is good or what is bad. In the real world, we might have like rewards sort of built into the physics of the actual world, like that's hot or that's cold, or that is painful or that is pleasurable. Some reward functions like that in the real world already exist. They're defined by our brains, etc. But if we talk about something like pathfinding, then the reward might be how far have I gone? Or if we're talking about a video game, it's how many points have I collected, for example. So we will have to define this reward function. Then we have some agent, whether or not that's represented by like a function, or it's a neural net, or it's a graph, or it's like a grid policy, or however. We'll talk about all that. We have some sort of agent. The agent is going to go through this training loop, maybe millions or billions of times, who knows, and it's going to get stronger and stronger and stronger. And then once we have trained our agent for long enough, we can now deploy that into some environment, right? And so we have our agent that is trained, and now I have a trained thing. So far we haven't given a ton of examples. Let me show you an example of a problem that is framed within the reinforcement learning framework. This is sort of one of the more famous examples in reinforcement learning. So this is called the cart pole problem. And the problem is you want to balance the pole on the moving base as long as possible, okay? Do I have anything that I can balance? No, I don't. So, I have, Jesus. This is bad. So I have a knife. Let's see if I can do this. All right. So I have this knife. This is the problem. Try and keep this balanced for as long as possible. Your actions are move left or move right. Okay, so if you're balancing it, oh Jesus, this is going to end terribly. How long can you keep it balanced? With a very short thing like this, that is very dangerous, not very long. So I won't do that anymore. I wish I had like a baseball bat or something. It's really easy to balance. So you've got this cart here is essentially your hand and you're moving it back and forwards, right? And the actions are move left and move right. And the rewards are, well, if my goal is to have the pole be balanced for as long as possible, then I'm going to give a positive reward of, let's say, +1 for each time step that it remains balanced. So if I keep it balanced for 6,000 milliseconds, and I'm doing states every 1 millisecond, then that would be a reward of 6,000, for example. If I only keep it balanced for 1 second, then that would be 1,000. So the reward directly reflects what you want to maximize. And in this case, it's the amount of time that the pole has been balancing. And this is called an episodic task. We'll get more into, we talked about an episodic task before, but we'll get more into what episodes mean within the context of reinforcement learning a bit later. And so episodic here meaning that this task eventually does end when the cart or when the pole falls, right? So at the very beginning, when we start our training, we may be very bad at balancing it. So maybe we only balance it for a half a second, but then we get a bit better and it's 2 seconds. Then maybe we're balancing for a minute, etc. And each of those instances of me starting to balance to where it falls off, that's called an episode. Here's another example. This is called the mountain car problem, and it's also a very, let me remove my camera for a second. This is also a very famous problem. And the problem here is we want to escape to the top of this valley as fast as possible. And so our actions are, I'm going to put the camera back on, but just realize this is the goal up here. So within this problem, we've got some physics simulation, right? So this kind of looks like the real world. I know the graphics are not as good, but if you just apply the gas, you are not going to be able to get up this hill because your engine isn't strong enough. But if you sort of apply the gas, and then as you're coming downward, you apply the reverse. And then as you're coming downward, you apply the gas. It's almost like being in a swing, right? Where you go, like you push in the direction that you're going, and you can eventually get out of this hill. So you can either accelerate to the left or accelerate to the right or backwards or forwards, however you want to view this problem. And since you want to get out of this as fast as possible, you can give a negative reward for each time step. So before, we wanted this to go on for as long as possible, so time was positively rewarded. But if we want to do something as quickly as possible, we can give a negative reward for each time step. So if we maximize a negative number, then we are effectively minimizing that number, which is the time to reach the goal. And this, again, is an episodic task where you would stop and start again once you reach the goal. So what we see over time is, okay, this is like in slow motion for some reason, but what we have is, as we go through more and more training episodes, we get better and better and better at the problem. And oftentimes what we'll do is we will have what we are trying to learn is a policy. We'll talk a lot more about policies in the future, but essentially we might start off with just random actions. I'm just going to do random things and see how they work. And based on the result of those random things, we start to get more and more certain about the outcomes of those actions and the type of rewards that they give us. And so over time, we learn which of those actions were good and which were bad within a given state, and then we can solve our problem a lot easier or a lot faster. Okay, so that's the whole process of reinforcement learning. But now let's get into the elements of reinforcement learning problems. So we got to have definitions, and I can promise you that there will be a final exam question that has to do with the definition of reinforcement learning problems, if not 2 or 3. So in order to form a reinforcement learning problem, first and foremost, we need the agent. Actually, just as important as the agent is the environment. So we have an agent, and we have some environment that the agent is acting in. We have a policy. That policy is going to be the thing that maps states of the environment to actions that we should perform. We're going to talk about that a lot more in the future. We have a reward function, which tells us, okay, if I take an action from my policy in a specific state of the environment, what is the reward that I get from doing that? Next, we have a value function, which the value function essentially says, how much do I like being in this state? Or how much do I like doing this action at this state? And then we also could have a model of the environment. So for example, if we are simulating one of these problems, right? If we have a computer simulation, then we essentially have a model of the environment. That model being the rules and the physics governing what is happening in the world. But we can also apply reinforcement learning to the real world with robotics, because you don't need to know the physics of the simulation in order to perform reinforcement learning. That is the biggest benefit of machine learning in general, is that you do not typically need a model of the environment in order to learn something about your actions or your input data. So a model of the environment is optional for reinforcement learning. Versus if I was to say do search, I need a model of the environment to do search, because I've got to be able to encapsulate a state and then transition to the next state and then be able to like rewind and go forward and back up. Like in order to do depth first search, breadth first search, A star, I need to have a model of my environment. It is necessary. So one of the main benefits of reinforcement learning is that it does not always need a model of the environment. Typically, if you do have a model, it can help you speed up things. Like for example, if you trained a reinforcement learning model on a real robot in the real world, then it might take a long time, right? Because you're constrained by the actual physical speed of that robot moving around. But if you had a model and you could simulate that robot moving around, maybe you could do 1,000,000 times more stuff per second as the real robot. So we know what an agent is. We know what an environment is. What are the other things? So what is a policy? A policy is a map from states of the environment to actions to be taken at those states. So it says, oh, look, here's the current state of the environment. What should I do? Should I move up? Should I move down? Should I move the queen diagonally? Should I jump on top of that Goomba? Should I touch the hot stove? That is all encoded by the policy. The policy, that mapping, might be a simple lookup table. So for example, at this hand of blackjack, I should hit or I should stick. Or it might be a complex computation, such as a neural network. How you encode the policy is up to you. And what we are going to be doing is we are going to be doing lookup table-based reinforcement learning. Since we use a table to store the policy, this is called tabular reinforcement learning. And we will talk about more complex forms of storing the policy at the very end of the reinforcement learning section. The policy is the core of the reinforcement learning agent because it defines the behavior of the reinforcement learning agent. Whenever we go to take an action, we have to look that up in the policy, okay? And the policy may be deterministic, it may be stochastic. So your policy might say, if I'm in this state, always move left. But your policy may also say, if you're in this state, always go, or 50% of the time you want to bet all in, 50% of the time you might want to fold if you're playing poker or something like that. So some optimal policies actually do contain random actions. And we'll also see that in assignment 5, there will be situations where, hey, moving left is just as good as moving right. So move left with 50% probability and move right with 50% probability. So how do we record the policy? Well, what is the terminology that we're going to use, or the syntax? So the policy is going to be represented by pi, the Greek symbol pi. So the policy at time step t, which means what should I do in a given state at a given time step, because our policy is going to change over time. right? So I've got a policy at time step 0. Then, once I've gotten a reward, I'm somehow going to update my policy because maybe now I think that something else is better to do. So my policy is now going to change for time step t+1. Well, it may not actually change, but the possibility of it changing is there. So the policy maps states of the environment to the probability of taking an action at that state. So pi sub t, saying the policy at time sub t of SA is the probability that my agent takes action A sub t, which is A, when state S sub t is equal to S, right? So again, this probability might be 1 or 0, or it might be anything in between. But it just says, in plain English, I'm at state S, and I'm at... Sorry, let me repeat that. I'm at state S. What is the probability that I should take action A? And that is encoded within the policy. And of course, policy pi sub t is recording the probability of doing action A sub t when state S is S sub t. Okay? So at any given time, what's the probability that I should do this action at this time step? Reinforcement learning methods, the algorithms that we are going to be looking at, they are going to specify how the agent changes its policy over time as it learns. So we know that there's going to be a policy. We don't yet know how we are going to represent the policy or how we are going to update the policy. The things that do that, representation and update, are called the reinforcement learning methods or the reinforcement learning algorithms. And the agent's goal is to form a policy that gets as much reward as it can over time. So as we will see in assignment 5, this is an example of a policy. I've got an environment here. Now, not all environments are so easily able to show a policy like this, but assignment 5 is specifically made to be as intuitive as possible. So here we've got an environment. It's similar to assignment 2. However, in this environment, we're only going to be walking around on the blank squares, and the dark squares are walls. And our goal is to get to one of these green squares as soon as possible. And so this is a snapshot of the optimal policy that we will learn. And it says, for example, if you are right here and you want to get to a green square as soon as possible, go up. If you're right here, well, it knows that going up and going left have equal value, so you can go to either of them. Similarly, if we have a blackjack as our problem, then you can say, if I'm over here at this state, if I have these cards and the dealer has these cards, then take this action. That is an example of a policy for blackjack. That's the policy. Now let's talk about rewards. So rewards define the goal in a reinforcement learning problem. And it maps each perceived state or state action pair to a single number. That's the reward. So it means this state action pair means every time I'm in this state, when I take an action, I'm going to get this reward value. So the reward is the desirability of a state. How, like, the desirability of, that's not true, actually. I'm going to remove that. That is not true. So reward comes from the environment. That is very, very important. The environment tells you what the reward was. You can't decide what the reward was. You can't just keep pumping yourself full of positive reward based on an action. The return is the sum of all the agent's rewards throughout an episode. Okay, so if you sum up all of the rewards, then that's the return. And your goal as an agent is to maximize return, not necessarily reward. So it's a long-term goal, right? Throughout the whole episode, how much reward did I get? So for example, there might be a time where there's an action that immediately gives me a better reward, but overall might give me a worse sum of all rewards or a worse return. And our goal is to maximize return for the agent. So in biology, the reward is how pleasurable or how painful is a particular action at a given state. So here's some examples of that. If we want to do pathfinding, typically we are wanting to minimize the distance or minimizing the time that we travel. So the goal might be the terminal state, and non-goal states have a -1 reward. And so here, getting to the goal the fastest maximizes the reward. It maximizes the return, because the path, the return of a particular path is the sum of the rewards of the path, and if we have -1s, then we want the shortest path. So that's what's going to happen. In blackjack, for example, or other card games, we may have a winning state is a positive reward. So if I took the action of hitting on 11, then I get a positive reward if I win. But if I keep hitting on 20, then I get a negative reward because I'll keep losing if I do that. And so the reward is going to be proportional to the amount of money that we won or lost based on like the rules of the game. Returns. So as I just said, the agent gets a reward at each time step, or t, t+1, t+2. The value that we want to maximize is the expected return. Expected just means the average return, right? Because sometimes we might get different rewards. The rewards are probabilistic. So we may get a reward one time we do something, we may not get the same reward another time we do something. For example, if I'm playing blackjack, if I have 20 and I hit, 90% of the time or more, I'm going to bust and lose. But there might be that one time in 15 or whatever the chances are that you get an ace and you get 21, right? So your rewards that you get from actions are not always the same because the rules of the game may involve chance. So the expected return essentially means that's the expected value of g of t, where g of t is the return. Okay, I don't know why they use the symbol g, but that's the symbol in the book, so I'm gonna stick with it. So g of t, excuse me, cat hair in the nose, is the sum of all future rewards, and t, capital T, is the final time step at the terminal state. So an optimal policy, and we like using star for optimal things, that is going to maximize the expected return. So that's what returns are. The value function. So rewards are what are immediately good. Excuse me just for 1 second. Oh, that's the wrong one. Just saving you me scratching my nose on camera. So rewards are what are immediately good. So if I take this action at this state, this is the reward that you will get. Value functions are going to indicate what may eventually be good or bad on expectation, okay? So the value of a state or a state action pair, so for the rest of this course, SA is going to mean taking action A at state S. It's a state action pair. That's the total amount of reward that an agent can expect to accumulate in the future if it's currently at that state, okay? So value indicates long-term desirability. So it's not an indication, it's correlated to immediate reward, but what it really is if I keep acting with this policy, what value do I place on being in that state, okay, over the long term? So if reward is pleasure or pain, value is how pleased or displeased we are to be here. So take an example like this. If you are falling a great distance, right, the reward of being in the state of falling might actually be positive, right? It's kind of fun to fall for a while. You might actually find that exhilarating. But eventually, you're going to stop falling and hit the ground, right? So if your brain is like, oh, falling is great, I love the reward that I get from being in the state of falling, value is going to recognize this fall is going to end eventually, and it's not going to be good for me. So the value of being in the state of falling is going to be very low because eventually you're going to hit the ground, right? But the reward of any particular state of falling may not be that bad. But we're eventually going to get that really negative reward right? So that's I think a good example. So we're going to seek the actions that have the highest value. Those will bring the highest eventual return. Value is harder to determine than reward because all you do is you sort of take samples. I'm going to try this action, watch the reward. Try this action, watch the reward. Well, I know exactly what the reward was, but I don't know what the value is because the value is this long-term thing that I have to calculate. So our policy ideally should have us take high-valued actions for each possible state. That's what our goal is take the highest valued actions, meaning the return. So value function examples in pathfinding. A non-goal state on the best path to the goal is going to have high desirability and a high value. And so the actions taking us on the path have high value, right? So if we're doing pathfinding, each individual action is going to be, for example, -1, right? Each action is going to give us the same reward each time, and that is a little bit of pain. You don't want to be walking. You don't want to be walking. You don't want to be walking. But what the value is the expected value of the return, which is the sum of the rewards, right? So a value at a particular state might be -15, for example, which means I think that I've got about 15 steps to go until the goal. So the value is the -15, the reward is the -1. And ideally, the actions that take us to more high-valued states are going to be more valued. Or in blackjack, me having 20 and the dealer showing a 6 has a high probability of winning, right? If I stick here, I'm probably going to win this situation 80% of the time. So it has a high value. So I want to be in that state because it's going to lead to high value. Let's talk about the model of the environment. The model of an environment would mimic the behavior of an actual environment. So a model would be, given that I'm in a given state and an action, the model is going to either attempt to predict the next state if we're doing something like modeling the real world, or if we've got like a game like Mario or chess, we're going to be able to exactly model that environment. Models are required for planning. They are required for this planning, these algorithms. Alpha, beta, A star, all those algorithms we talked about before, models are required. But they are not necessary for reinforcement learning in general, but they are often used, if they can be, in order to help speed things up and help the training process. So for example, you can completely learn how to play chess without knowing the rules of chess. It's possible. You just take a bunch of actions and you record which ones were good and which ones were bad, and you don't have to know why they were good or bad, in theory, but if you know what the rules are, you could do that to, say, play against yourself, right? And really speed up the learning process. So models are not required, but they are sometimes useful. Now we get into the real meat of reinforcement learning, which is exploration versus exploitation. And this is one of the main challenges in reinforcement learning, is the trade-off between exploration and exploitation. And you bet you that this is going to be an exam question. So you're going to learn a lot about this problem. To obtain a lot of reward, agents must prefer actions that it knows produce good results. But in order to learn which actions produce good results, it has to try them first, right? So the agent must exploit knowledge that it has, but it also has to explore in order to gain that knowledge. And in my opinion, this is one of the main challenges of real life, too. Like, for example, I think the best possible example of this for real life is, what's your favorite restaurant, right? Where are we going to go to eat tonight? What are we going to have to eat? Well, I'm a big fan of Wendy's, right? So my go-to cheap meal is going to be Wendy's. I am exploiting my knowledge that a junior bacon cheeseburger is pretty delicious. So I'm going to try it. But maybe there's another restaurant out there that I've never tried that has something more delicious for the same price, right? So, but in order to do that, I have to explore. So part of my training is going to involve taking actions that may not be good, but I don't know if they're good yet. So I have to exploit what I know is good, but also explore to gain more knowledge. And that's a huge, huge, important thing, again, not only in reinforcement learning, but in real life. So that's the example, right? Going to a restaurant. You can go to the place that you know is all right, or try a new place that you've never eaten before. Also, playing games. I chose door number 3 last time, and it had 10 gold pieces. So this is like an exact problem that we're going to deal with in the next lecture. If you have 3 doors in front of you, you chose one and it gave you 10 gold. Are you going to choose it next time and get the 10 gold again? Or choose door number 1. Maybe door number 1 has a demon behind it that will kill you, or it might have 1,000 gold pieces, right? How are you going to figure out which thing to choose? And another example, there's no more slides, so I kind of want to end you off on this example, which is a bit controversial, but also something to think about. Let's say someone came to you in real life and said, man, I ate at McDonald's and I really liked it. I liked McDonald's. That's okay. So that's not the controversial part, but they said, I ate at a single restaurant, whatever that single restaurant might be, and I liked it. So I'm never going to eat anything else for the rest of my life. I tried something, I liked it, therefore I'm sticking with that place forever. You'd call them crazy, wouldn't you? You would say, hey, you are absolutely crazy. That is an insane decision. But what if we said the same thing about relationships? Right? How many people out there are eating at the same restaurant for the rest of their lives forever after only trying one restaurant? So I understand that the problem is a little bit different, but I always like to include that because it's just a really interesting example. Now, the reason it's not the same is because if you go eat at Wendy's after eating at McDonald's, McDonald's isn't going to kick you out, right? But it's a little bit harder to try new restaurants in the relationship world. So anyway, just to keep something in mind. That is exploration versus exploitation. We will go into much more detail about this in the future, talk about the mathematics behind it, and how we will use that for reinforcement learning in the future. All right, that is it for this lecture. I could have squeezed in a little bit of mathematics, but I'm just going to leave that until the next lecture and sort of leave the cliffhanger there of how cool reinforcement learning is. And we'll come back the next time and talk about bandit algorithms, which are really at the heart of reinforcement learning. So thank you so much for tuning into this lecture, and there's no questions out there, so I'm going to end it there, and I'll see you in the next lecture on Tuesday.